Today on UPSC Geography View, as climate changes ravel all over the world and rapidly rotating storm systems are frequent over coastal areas in every continent, it is now more important than ever to understand what tropical cyclones are. Hello and welcome to UPSC Geography View at UPSC Practice. Let's learn about tropical cyclones. Tropical cyclones are a rapidly rotating storm system characterized by a low pressure center, a closed low-level atmospheric circulating, strong winds, and a spiral arrangement of thunderstorms that produce heavy rain or squalls. Depending on its location and strength, a tropical cyclone is referred to by different names, including hurricane, typhoon, tropical storm, cyclonic storm, tropical depression, or simply cyclone. A hurricane is a tropical cyclone that occurs in the Atlantic Ocean and northeastern Pacific Ocean, and a typhoon occurs in the northwestern Pacific Ocean, in the South Pacific or Indian Ocean. Comparable storms are referred to simply as tropical cyclones or severe cyclonic storms. Tropical refers to the geographic origin of these systems, which forms almost exclusively over tropical areas. Cyclone refers to their winds moving in a circle, whirling around their central clear eye, with their winds blowing counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The opposite direction of circulation is due to the Coriolis effect. Tropical cyclones typically form over large bodies of relatively warm water. They derive their energy through the evaporation of water from the ocean surface, which ultimately recondenses into clouds and rain when moist air rises and cools to saturation. This energy source differs from that of mid-latitude cyclonic storms, such as northeasters and European windstorms, which are fueled primarily by horizontal temperature contrasts. Tropical cyclones are typically between 100 to 2000 kilometers in diameter, or 60 to 1240 miles. Every year, tropical cyclones impact various regions on the globe, including the Gulf Coast of North America, Australia, India, and Bangladesh. The strong rotating winds of a tropical cyclone are a result of the conservation of angular momentum imparted by the Earth's rotation as air flows inwards toward the axis of rotation. As a result, they rarely form within 5 degrees of the equator. Tropical cyclones are almost unknown in the South Atlantic due to a consistently strong wind shear and a weak intertropical convergence zone. Conversely, the African easterly jet and areas of atmospheric instability give rise to cyclones in the Atlantic Ocean and Caribbean Sea, while cyclones near Australia owe their genesis to the Asian monsoon and Western Pacific warm pool. The primary energy source for these storms is warm ocean waters. These storms are therefore typically strongest when over or near water and weaken quite rapidly over land. This causes coastal regions to be particularly vulnerable to tropical cyclones compared to inland regions. Coastal damage may be caused by strong winds and rain, high waves due to winds, storm surges due to wind and severe pressure changes, and the potential of spawning tornadoes. Tropical cyclones draw in air from a large area and concentrate the water content of that air from atmospheric moisture and moisture evaporated from water into precipitation over a much smaller area. This replenishing of moisture-bearing air after rain may cause multi-hour or multi-day extremely heavy rain up to 40 kilometers from the coastline, far beyond the amount of water that the local atmosphere holds at any one time. This in turn can lead to river flooding, overland flooding, and a general overwhelming of local water control structures across a large area. Although their effects on human populations can be devastating, tropical cyclones may play a role in relieving drought conditions, though this claim is disputed. They also carry heat and energy away from the tropics and transport it towards temperate latitudes, which plays an important role in regulating global climate. Let's look at the background of a tropical cyclone. A tropical cyclone is the generic term for a warm-cored, non-frontal, synoptic scale, low-pressure system over tropical or subtropical waters around the world. The systems generally have a well-defined center which is surrounded by deep atmospheric convection and a closed wind circulation at the surface. Historically, tropical cyclones have occurred around the world for thousands of years, with one of the earliest tropical cyclones on record estimated to have occurred in Western Australia in around 6000 BC. However, before satellite imagery became available during the 20th century, many of these systems went undetected unless it impacted land or a ship encountered it by chance. These days, on average, around 80 to 90 named tropical cyclones form each year around the world, over half of which develop hurricane force winds of 65 knots, that is 120 km per hour or 75 miles per hour or more. Around the world, a tropical cyclone is generally deemed to have formed once mean surface winds in excess of 35 knots or 40 miles per hour are observed. It is assumed at this stage that a tropical cyclone has become self-sustaining and can continue to intensify without any help from its environment. Let's learn about the structure of a tropical cyclone. Tropical cyclones on either side of the equator generally have their origins in the intertropical convergence zone, where winds blow from either the northeast or southeast. Within this broad area of low pressure, air is heated over the warm tropical ocean and rises in discrete parcels, which causes thundery showers to form. These showers decimate quite quickly, however, they can group together into large clusters of thunderstorms. This creates a flow of warm, moist, rapidly rising air, which starts to rotate cyclonically as it interacts with the rotation of the Earth. There are several factors required for these thunderstorms to develop further, including sea surface temperatures of around 81 degrees Fahrenheit, that is 27 degrees Celsius, and low vertical wind shear surrounding the system. The first important significant feature of the structure of a tropical cyclone is the eye and center. At the center of a mature tropical cyclone, air sinks rather than rises. For a sufficiently strong storm, air may sink over a layer deep enough to suppress cloud formation, thereby creating a clear eye. Weather in the eye is normally calm and free of convective clouds, although the sea may be extremely violent. The eye is normally circular and is typically 19 to 40 miles or 30 to 65 kilometers in diameter, though eyes as small as 1.9 miles or that is 3 kilometers and as large as 230 miles or 370 kilometers have been observed. The cloudy outer edge of the eye is called the eye wall. The eye wall typically expands outward with height, resembling an arena football stadium. This phenomena is sometimes referred to as the stadium effect. The eye wall is where the greatest wind speeds are found. Air rises most rapidly, clouds reach their highest altitude, and precipitation is the heaviest. The heaviest wind damage occurs where a tropical cyclone's eye wall passes over land. In a weaker storm, the eye may be obscured by the central dense overcast, which is the upper level cirrus shield that is associated with a concentrated area of strong thunderstorm activity near the center of a tropical cyclone. The eye wall may vary over time in the form of eye wall replacement cycles, particularly in intense tropical cyclones. Outer rain bands can organize into an outer ring of thunderstorms that slowly moves inward, which is believed to rob the primary eye wall of moisture and angular momentum. When the primary eye wall weakens, the tropical cyclone weakens temporarily. The outer eye wall eventually replaces the primary one at the end of the cycle, at which time the storm may return to its original intensity. Let's see about the interaction with the upper ocean of a tropical cyclone. The passage of a tropical cyclone over the ocean causes the upper layers of the ocean to cool substantially, which can influence subsequent cyclone development. This cooling is primarily caused by wind-driven mixing of cold water from deeper in the ocean with warm water surface. This effect results in a negative feedback process that can inhibit further development or lead to weakening. Additional cooling may come in the form of cold water from falling raindrops. Cloud cover may also play a role in cooling the ocean by shielding the ocean surface from direct sunlight before and slightly after the storm passage. All these effects can combine to produce a dramatic drop in sea surface temperature over a large area in just a few days. Conversely, the mixing of the sea can result in heat being inserted in deeper waters with potential effects in global climate. Let's explore the movement of a tropical cyclone. The movement of a tropical cyclone, that is its track, is typically approximated as the sum of two terms: steering by the background environmental wind and beta drift. Let's see the environmental steering. Environmental steering is the primary influence on the motion of tropical cyclones. The environmental steering represents the movement of the storm due to prevailing winds and other wider environmental conditions similar to leaves carried along by a stream. Physically, the winds or flow field in the vicinity of a tropical cyclone may be treated as having two parts: the flow associated with the storm itself and the large-scale background flow of the environment. Tropical cyclones can be treated as local maxima of vorticity suspended within the large-scale background flow of environment. In this way, tropical cyclone motion may be represented to first order as advection of the storm by the local environmental flow. This environmental flow is termed the steering flow and is a dominant influence on tropical cyclone motion. The strength and direction of the steering flow can be approximated as a vertical integration of the winds blowing horizontally in the cyclone's vicinity, weighted by the altitude at which those winds are occurring. Because winds can vary with height, determining the steering flow precisely can be difficult. The pressure altitude at which the background winds are most correlated with the tropical cyclone's motion is known as the steering level. The motion of stronger tropical cyclones is more correlated with the background flow averaged across a thicker portion of troposphere compared to weaker tropical cyclones whose motion is more correlated with the background flow averaged across a narrower extent of the lower troposphere. When wind shear and latent heat release is present, tropical cyclones tend to move towards regions where potential vorticity is increasing most quickly. Climatologically, tropical cyclones are steered primarily westward by the east to west trade winds on the equatorial side of the subtropical ridge, a persistent high pressure area over the world's subtropical oceans. In the tropical North Atlantic and Northeast Pacific Oceans, the trade winds steer tropical easterly waves westward from the African coast towards the Caribbean Sea, North America, and ultimately into the Central Pacific Ocean before the waves dampen out. These waves are the precursors to many tropical cyclones within this region. In contrast, in the Indian Ocean and Western Pacific in both hemispheres, tropical cyclogenesis is influenced less by the tropical easterly waves and more by the seasonal movement of the intertropical convergence zone and the monsoon trough. Other weather systems such as mid-latitude troughs and broad monsoon gyres can also influence tropical cyclone motion by modifying the steering flow. Next comes the beta drift. In addition to environmental steering, a tropical cyclone will tend to drift poleward and westward, a motion known as beta drift. This motion is due to the superposition of a vortex, such as a tropical cyclone, onto an environment in which the Coriolis force varies with latitude, such as on a sphere or beta plane. The magnitude of the component of tropical cyclone motion associated with the beta drift ranges between 1 to 3 meters per second and tends to be larger for more intense tropical cyclones and at higher latitudes. It is induced indirectly by the storm itself as a result of a feedback between the cyclonic flow of the storm and its environment. Physically, the cyclonic circulation of the storm advects environmental air poleward east of center and equatorial west of center. Because air must conserve its angular momentum, this flow configuration induces a cyclonic gyre equatorward and westward of the storm center and an anticyclonic gyre poleward and eastward of the storm center. The combined flow of these gyres acts to advect the storm slowly poleward and westward. This effect occurs even if there is zero environmental flow. Due to a direct dependence of the beta drift on angular momentum, the size of a tropical cyclone can impact the influence of beta drift on its motion. Beta drift imparts a greater influence on the movement of a larger tropical cyclones than that of smaller ones. Let's take a look at multiple storm interaction scenario. A third component of motion that occurs relatively infrequently involves the interaction of multiple tropical cyclones. When two cyclones approach one another, their centers will begin orbiting cyclonically about a point between the two systems. Depending on their separation distance and strength, the two vortices may simply orbit around one another or else may spiral into the center point and merge. When the two vortices are of unequal size, the larger vortex will tend to dominate the interaction and the smaller vortex will orbit around it. This phenomena is called the Fujiwara effect after Sakuhei Fujiwara. Let's see the interaction of tropical cyclones with the mid-latitude westerlies. Though a tropical cyclone typically moves from east to west in the tropics, its track may shift poleward and eastward either as it moves west of the subtropical ridge axis or else if it interacts with the mid-latitude flow, such as the jet stream or an extratropical cyclone. This motion, termed recurvature, commonly occurs near the western edge of the major ocean basins, where the jet stream typically has a poleward component and extratropical cyclones are common. An example of tropical cyclone recurvature was Typhoon Ioke in 2006. Size of a cyclone. There are a variety of metrics commonly used to measure storm size. The most common metrics include the radius of maximum wind, the radius of 34 knot wind, that is gale force, the radius of outermost close isobar or ρc, ROCI, and the radius of vanishing wind. An additional metric is the radius at which the cyclone's relative vorticity field decreases at the rate of 1 into 10 to the power minus 5 per second. On Earth, tropical cyclones span a large ranges of size, from 100 to 2000 kilometers, as measured by the radius of vanishing wind. They are largest on average in the Northwest Pacific Ocean Basin and smallest in the Northeast Pacific Ocean Basin. If the radius of outermost closed isobar is less than 2 degrees of latitude, that is 138 miles, then the cyclone is very small or a midget. A radius of 3 to 6 latitude degrees, that is 207 to 416 miles, is considered average sized. Very large tropical cyclones have a radius of greater than 8 degrees or 552 miles. Observations indicate that size is only weakly correlated to variables such as storm intensity, that is maximum wind speed, radius of maximum wind, latitude, and maximum potential intensity. Let's learn about rapid intensification of a tropical cyclone. On occasion, tropical cyclones may undergo a process known as rapid intensification, a period in which the maximum sustained winds of a tropical cyclone increase by 30 knots or more within 24 hours. For rapid intensification to occur, several conditions must be in place. Water temperatures must be extremely high, near or above 30 degrees Celsius or 86 degrees Fahrenheit, and water of this temperature must be sufficiently deep such that waves do not upwell cooler waters to the surface. On the other hand, tropical cyclone heat potential is one of such non-conventional subsurface oceanographic parameters influencing the cyclone intensity. Wind shear must be low. When wind shear is high, the convection and circulation in the cyclone will be disrupted. Usually, an anticyclone in the upper layers of the troposphere above the storm must be present as well. For extremely low surface pressures to develop, air must be rising very rapidly in the eye wall of the storm, and an upper level anticyclone helps channel this air away from the cyclone effectively. However, some cyclones such as Hurricane Epsilon have rapidly intensified despite relatively unfavorable conditions. Dissipation of a tropical cyclone. There are a number of ways a tropical cyclone can weaken, dissipate, or lose its tropical characteristics. These include making landfall, moving over cooler water, encountering dry air, or interacting with other weather systems. However, once a system has been declared dissipated or lost its tropical characteristics, its remnants could regenerate a tropical cyclone if environmental conditions become favorable. Landfall of a tropical cyclone. Should a tropical cyclone make landfall or pass over an island, then its circulation could start to break down, especially if it is a mountainous island. Should a system make landfall on a large landmass, It would be cut off from the supply of warm, moist maritime air and would start to draw in dry continental air. This, combined with the increased friction over land areas, leads to the weakening and dissipation of the tropical cyclone. Over a mountainous terrain, a system can weaken quickly. However, over flat areas, it may take 2 to 3 days for the circulation to break down and dissipate. What are the factors of dissipation of a tropical cyclone? A tropical cyclone can dissipate when it moves over water significantly cooler than 80 degrees Fahrenheit or 27 degrees Celsius. This will cause the storm to lose its tropical characteristics, such as a warm core with thunderstorms near the center, and become a remnant low-pressure area. These remnant systems may persist for up to several days before losing their identity. This dissipation mechanism is most common in the eastern North Pacific. Weakening or dissipation can also occur if it experiences vertical wind shear, causing the convection and heat engine to move away from the center. This normally ceases development of a tropical cyclone. In addition, its interaction with the main belt of the westerlies by means of merging with a nearby frontal zone can cause tropical cyclones to evolve into extratropical cyclones. This transition can take 1 to 3 days. Artificial dissipation of a tropical cyclone. Over the years, there have been a number of techniques considered to try and artificially modify tropical cyclones. These techniques have included using nuclear weapons, cooling the ocean with icebergs, blowing the storm away from land with giant fans, and seeding selected storms with dry ice or silver iodide. However, these techniques have failed to appreciate the duration, intensity, power, or size of tropical cyclones. Thank you very much for listening to this discussion on tropical cyclones. For more such discussions, get the UPSC Practice app from the App Store.